Well, hey everyone. Just want to give you a thanks and thumbs up. Just surpassed 100 subscribers. Only took me a year and a half to get that far. So yeah, don't get a lot of views or anything, but anyway, thanks for all the subscriptions. And hopefully my videos are at least somewhat entertaining or educationable. Word I made up. But anyhow, got some more stuff to talk about. Well, I'm going to try shooting with my better camera. I normally can't use this because when I use a movie maker, my video gets all, when I move around, it gets choppy. I don't know if it'll do it this time or not. I just gave up on it. I gotta find myself a better video editor, try something out. I'm just lazy and never get around to that stuff. Here's the camera I normally use. It's a $30 Craigslist find I bought like 3 years ago, I guess, and I use that for most of my videos. Cleaned up my workbench a little bit. Kind of been playing around, so it's getting messy again. And it's lunchtime. It's kind of crappy out today, rainy, overcast. Yet my solar panel is still powering up my LEDs. Not super bright or anything, but yeah, it lights it up pretty good. Well, my sidekick is taking over the chair here, so I'm going to have to sit on the very edge and do this video. So what I'm trying to do today is see if I can speed up the slow transistor. Well, I look at the data sheet. It's a BC337, and transition frequency is 100 megahertz. And you know, you should be able to use it in the up to 10 megahertz with some reasonable gain. However, there's a problem I run into. I'm using it on the output of this Pickaxe microcontroller. The controller is programmed to put out a 1 megahertz square wave, which feeds the transistor. Here's the microcontroller. Feeds the base of the transistor through this resistor, and the transistor collector is fed from a separate power supply. It goes through the 100 ohm load resistor here and goes through the transistor. Well, let's see what issues I have here. Well, I have the blue channel hooked up to the collector of the transistor, the output, and the yellow channel is the output of the Pickaxe microcontroller. So let me turn on the power supply to the transistor. Set for 6 volts, and it jumped up 6 divisions, so it's set for 1 volt per division. And you know, nothing is turned on yet. The microcontroller is still turned off. So because the transistor is not conducting, we see that full power supply voltage on the collector. I'll plug in the batteries to the battery supply, which supplies the microcontroller, and that goes into the positive connector there. And look what happens. Well, this is the output from the microcontroller, putting the square wave, 1 megahertz square wave, into the base of that transistor. And look what happens. The transistor now turns on, turns fully on, and there's probably a couple millivolts. You know, that's just a collector emitter voltage drop. It's not switching or anything. So again, this is now inputting that square wave into the base. The transistor just turns on. It's not switching on and off like I want it to. So what's the problem here? Well, I remember reading that when you saturate a transistor, it slows it down because there's excessive charge carriers in the base region, and they don't clear out fast enough for the transistor to, start switching on and off with the original signal. But there are a couple little tricks you can do to make it switch faster. One way is attaching a signal Schottky type diode in this manner from the base to collector. Now if you look at this thing, you go, how in the heck would this possibly make it switch faster? Well, what happens is the transistor is fully turned on, so there's only a few millivolts across the the collector to emitter junction. So what this does is divert some of the signal around and sends it through the transistor like this. And because the voltage drop across the Schottky type diode is lower than this junction here, the base to emitter junction, it doesn't allow the transistor to saturate fully because it doesn't let this voltage come all the way up. Another way you can do this is use two silicon diodes, switching type, but because of the higher voltage drop, if you just use one here instead of the Schottky diode, well, the voltage drop is the same and you don't get any benefit, so you have to increase the voltage drop by adding a forward bias diode right here between where this one connects and the base. But since I have some Schottky diodes, I just put one here. Okay, let me connect the diode between the base and emitter junction. I mean the collector, base and collector, is what I'm trying to say. And I think I got that. Look what happens, it's now switching. But it's only switching about halfway. It's kind of a sloping turn on. It switches and turns off. Well, I can improve that by adding a resistor from here to ground. And let me grab my resistor and plug it in here. Okay, I added this resistor from base to ground. It is 470K. This one is 1K kilo ohm resistor. So now with that resistor, it's shunting more of that signal output from the microcontroller to ground. And look at that, switching pretty good now. I might be able to tune it and get it even better, but that's doing pretty good. Now you might be saying, why is it out of phase with the original signal? Well, you have to remember, when the microcontroller turns on, the output turns on or goes high, the transistor turns on, and when it turns on, it's shunting the current now through the transistor to ground, so it pulls it low. So as you can see, when this turns on, this goes low. When the microcontroller output turns off, it goes back high because it's not conducting anymore. So there you have it. That's how you can speed up your transistor in a switching circuit. Of course, another way you can do it is just not have it saturate at all, but you can run into issues with heat dissipation and all that stuff. But that's it. Just wanted to show you what a Baker clamp type circuit is. Thanks for watching.